Welcome back, folks. Today we're going to be talking about object recognition, and we're going to be looking at CVAA chapters 6.1, 6.2.1, and 7.1. So for object recognition, what we're trying to do is label what's seen in some image. There's many different variations of the recognition task, including classification, retrieval, and pose recognition, as well as things like attribute prediction and hierarchical classification. In all of these, what we're trying to do is match some aspect of the image into some set of categories or poses. Now, we're going to be looking at some fairly straightforward machine learning techniques for doing object recognition. These are somewhat on the classical side of things. Object recognition is very much dominated by machine learning approaches, and once we start getting more deeply into more advanced machine learning techniques, we'll start to talk about more modern approaches for doing object recognition. But still, the techniques that we'll talk about today are very much in active use and are still quite useful. So the major challenge in dealing with object recognition is that we're trying to go from images, which are these massive arrays of pixels, down to a few classes of objects. So what we want to do is somehow convert these arrays into, for example, just a label of whether this is a cup of a frosty beverage or a chair, for example. In the classic computer vision pipeline, the general approach for dealing with images is to take these pixels and convert them into some sort of higher level features. These could be, for example, edges or corners in the image. And then we can take these low level features and we could perhaps cluster them into certain kinds of regions of the image which correspond to parts. Then we might want to take those parts and convert them into identities. So essentially this kind of pipeline of going from very low level, fine-grained components of an image to higher level understanding is usually done with this kind of fixed pipeline. Now this contrasts with the modern approach to dealing with object recognition, which is to just use deep learning for everything, and rather than having a fixed pipeline, have essentially learning do every single component of this pipeline. Now we'll talk about that more in a couple of weeks, but for now let's talk about the classical computer vision pipeline, which is represented by certain software libraries like OpenCV. So one very straightforward way to try to recognize objects is known as either patch matching or template matching. So the idea is that we have some sort of source object that we'd like to identify in some target image. And so what we'll want to do is find some patch in that source, find a similar patch in that target image, and to characterize whether or not that's a good match, we'll use some sort of error function, so for example the sum of squared pixel differences, to determine whether this is a good match or not. Once we've determined whether certain patches match in one part of the image versus the other, we'll then do something with those matches. Whether it's dense stereo reconstruction, such as what I'm showing here on the left, or doing pose estimation, such as what I'm showing on the right, you can do something with those matches to try to accomplish some downstream task. So in the case of stereo reconstruction, it's certainly looking at small patches. So these, the source image and the target image, they're looking at usually fairly small, ranging from 5 to 20 pixel squares from one image to another. And so this type of matching is done throughout the entire image, giving you what's known as a disparity map. Basically, how much do I have to shift one patch to find the best match in the other patch? Now, for doing things like pose recognition, what you can do is, for example, render lots of different images of the target object from different viewpoints, and then you can try to find that template image that you'd see from that viewpoint in your target image. And doing so can try to then map back to the pose of the object, from that rendered viewpoint. So in any case, what we're doing is we're building associations. And another way that we can build associations in a somewhat more effective way, more efficient way than doing a brute force template match is something called feature recognition. This is a classical sort of pipeline. It was certainly more popular 10 years ago, but it's still state-of-the-art for many robotics tasks. So the idea is that we want to find some distinctive pixels. So basically, rather than looking at all patches or the entire image at once, we're going to focus on a few key features, so a few key points in the image. we'll then look only at patches around each of those features to describe the features in some way, and then we'll try to find matches in your target image. And then again, we'll do something with those matches. So how do we do this? So the key thing here is the feature extraction component. And the reason why we want to use feature extraction is that, in images, there's certain areas that have very distinctive appearance. And these are areas like corners and high texture areas that we can associate clearly with another component of the other image. So here's two pairs of images of a mountain scene. You can see that this part, there's a sort of sky component in the left image and the right image that seems to be somewhat matched, but they don't really look visually distinctive. And so, this has a very kind of flat appearance. You're not going to be able to distinguish this patch of sky from any adjacent patch of sky. The area on the bottom right here is a bit better. This is a piece of shadow, and you can see that this curve that rapidly transits from light to dark, can be discovered in the other image, reasonably accurately. But there's still some possibility for confusion. Now this little tip over here, this little tip of the peak with this patch of snow is a very distinctive patch, and you can very clearly match this patch to the patch on the right image. So we're really looking for these sharp gradients in the image where the parts of the image change, the pixels of the image change intensity rapidly. So one way of trying to represent this sort of goodness of a feature is to look at what's known as the autocorrelation of the image. So autocorrelation looks at how the image looks like itself, but shifted by some number of pixels. So if we represent I of x as the image intensity at a certain pixel, then what we're doing is taking some delta u, some shift in the patch, and we're looking to see how well does the one patch match against the other one. And when these patches are identical, this autocorrelation function is going to be 0. But when they differ quite a bit, it's going to be high. And what we want to have is a strong peak of this autocorrelation function, such as the bottom right image, which is marked by a little red cross down in that highly textured area in the front. So this is, for example, much better than looking at the sky, which has very little autocorrelation, and this kind of edge up here at the upper right has some autocorrelation in certain dimensions, but we're not necessarily going to be able to distinguish that patch from another patch that's translated along that edge. Okay, so how do we do that? So there are many different types of feature description techniques, and two of them, which are very related, are called Harris features or Shitamase features. The idea is that we can try to approximate this autocorrelation function using its first order Taylor expansion. And if we were to calculate out all of the math, the idea is that we can approximate the shape of this function as a quadratic function that is centered about 0. So at 0 you have 0 error between your patch and itself, but then as you go away from the patch you have higher error, and so this approximates this matrix M here, which is the sum of the outer products of image gradients, becomes a representation of your feature. So if you were to look at these particular points in the image, if you look at the isosurfaces of the level sets of these quadratic functions, you'd see that the sky has a very kind of broad base of support. That means it doesn't go up sharply very quickly. The edge has a kind of very elongated, directional sharpness, but this point in the bottom has a nice sharp peak. So we would like to figure out some way of measuring how peaky this matrix actually is, how peaky this quadratic bowl is. So both the Harris and Shitamase features use the eigenvalues of this matrix. This is a 2 by 2 matrix. The Harris feature has this expression over here. It has a parameter k. Shitamase features just take the minimum of the two. And the idea is that we want to have large values to get good features. So things that are giving us peaky quadratic approximations of this autocorrelation. Okay, so then supposing we have such a scoring metric, we'll find endpoints that are local maxima of the scoring metric. Why do we want local maxima rather than just picking the top n pixels? Well, there's a good reason for this. So if we were to just look at certain areas, certain very textured areas, those will have really strong features. They'll have high scores. And we don't necessarily want to put points all in these highly featured areas. We might want to actually distribute them across the image. So, and also we might not just want to pick the top n local maxima too. So these local maxima might be highly concentrated in certain areas of the image. So this gives rise to a technique that's very often used in computer vision called adaptive non-maximal suppression. So if you're to just look at the top n features for this Notre Dame image, you see that there's a lot of concentration near these kinds of corner points. Adaptive non-maximal suppression takes let's say you take the top feature point, you then suppress this feature scoring metric in a small neighborhood about that point, so you don't produce more feature points very close to feature points that you've already produced. And in this, you get a much more uniform distribution of these feature points across your image. Now, let's say that I produce this set of features for two different images. Now, I want to try to match them together and see whether or not this source image and target image match. The basic approach for doing this is to try to figure out which features in the source image match to the target image. And so what we do is we convert the patch of the image around that feature point into a vector of fixed dimension. And so we then do just some sort of simple matching like nearest neighbors to try to determine whether a part of image 1 corresponds with a part of image 2. Keep in mind that we're, for example, trying to find an object in a cluttered scene. We've seen the object in isolation. Now we want to see it with a bunch of background. We're not going to see all of the features matching directly to one another, but we'll see that some of them will match. So the hope is that we can do, for example, we can find some subset of these features which match together. And if I have a sufficient number of matches, I can say that I've found a full match of the source object in the target scene. Now, how do we choose these features, what do the features actually say? So one of the problems of just using, for example, the pixels of a source patch is that we end up making poor decisions about which matches we actually have. So for example, we've seen an object in a very nice illuminated environment, and then our target image is not so well illuminated. There can actually be a very large pixel difference between those features just because one is light, one is dark. So people have spent a lot of time trying to come up with good feature descriptions that ignores information that's irrelevant to object identification. So for example, translation, orientation, scale, and lighting. And so many of these types of feature descriptors, including Sift, Hog, ORB, etc., try to represent what the image looks like in this patch around a given feature in a way that can let it identify the same object under a variety of different of conditions. So as an example, rather than just vectorizing the patch of pixels, Sift features, which stands for Scale Invariant Feature Transform, does a procedure that is more sensitive to the gradients of the image in that patch. It takes a 16 by 16 patch, it takes the gradients of the image in those patches, it then bins them into quadrants and then bins them into these histograms and does some other stuff to try to build in more robustness. So in the end of this procedure, you get a 128-dimensional feature description vector, which is invariant to certain scaling and lighting transformations. So from this, we then have a 128-dimensional space, and we want to figure out how close these features are to one another. If our feature transforms were performed in a way that allows us to just use Euclidean distance, then we can just look, for example, at the closest match. But we still have to tune the radius of the matching. Now, if we have a different type of feature transform and we don't know that things are essentially isotropically equivalent, we might want to scale each axis to get a better matching. So for example, if I were to change the scaling so that the up and down axis here has a lower weight than the left and right axis, I might match the top image 2 features to the bottom image 1 features over there. And so this may or may not be what we want, and the question is, how do we then come up with the weightings, come up with these radiuses to get good performance? And this gives us a kind of glimpse into some introductory machine learning. So what we'll need to do is have some sort of a data set of ground truth feature matches. So for example, we can have humans go ahead and label what things are actually matching to one another. Then for a given set of parameters to this matcher, I can calculate the number of false positives and false negatives, and then I can tune its parameters to improve the number of false positives and false negatives. So just to be perfectly clear, a false positive is when a match is detected by the feature detector, but it's actually no match. A false negative is the opposite, where the detector does not detect a match that is actually a true match. And then we have true positives and true negatives, which are the correctly determined matches and non-matches. So from this ground truth, I can compare the fraction of true positives, fraction of false positives, fractions of false negatives, and fraction of true negatives. And this can be arranged in this kind of data can be arranged in a matrix form called the confusion matrix. Now, to summarize the false positive rate, false negative rate, I can actually convert this down to 2 features rather than 4. These are known as precision and recall. Precision is the number of true positives divided by the number of true positives and the number of false positives. So this is the number of true positives that exist in the things that I return as matches. The recall is trying to measure the false negative rate. So it's the number of true positives divided by the number of true positives and false negatives. So this is the number of true positives that I've detected correctly divided by the number of positives in the ground truth data set. So in other words, a high precision detector is one that's selective. It's going to produce matches that actually are true matches, but it may miss some matches that are actually true matches, but we prioritize the precision of this classifier. The alternative is a high recall detector, which is going to be inclusive. So it will produce as many matches as possible. It will produce many matches, but also possibly some false positives. Okay, so we can then use these 2 numbers to tune how we want our classifier to behave. So let's suppose that the true matches are the ones that are circled here in blue, and I were to, for example, be trying to tune the matching radius of a nearest neighbor classifier. So if I have a match radius of 0, I don't produce any matches, and my precision is 1 because, well, I haven't returned anything, so everything I return is, well, it's a true match, but I don't return anything. The recall, though, is 0 because I don't return any of the true matches. Now, if I have a small radius, I could get, for example, if I, in this case, get 2 of the true matches correct, but I don't get 1 of the true matches correct. In this case, my precision is 1 because every single match that I return is a true match, but my recall is only 2 out of 3. If I increase my matching radius, then I will have included this term, this match down here at the bottom, and I still have those 2 original true matches that I've gotten correct. But this false positive here reduces my precision down to 2/3, while my recall is still 2/3 because I'm only returning 2 of the true matches, which are out of 3. Now, if I increase my radius larger, I now have the true match here that I hadn't had before. So my recall is actually 1. I've produced all of the matches that actually exist in the ground truth, but my precision is at 3/4 because I'm still returning that false positive down at the bottom. Now, if I have the match radius to be quite large, I'll have a lot of a very high recall because I'm returning lots of matches, but my precision is quite low because now I'm returning lots of matches that don't actually exist. Now, if you think about tuning this parameter on a continuous basis, you can think about tracing out a curve in the precision recall space. So on one axis is precision, the other one is recall, and the optimal performance is going to be in the upper right corner at 1,1 precision and 1,1 recall. Now, for a given predictor, if I were to tune this, I'll get a curve. A better predictor is one that gives me a precision recall curve that gets closer to that upper right corner 1, 1. Now, if I have a given classifier and I want to figure out where I'd like to be in terms of tuning that parameter, I might want to have very high recall if I'm trying to, for example, get more matches, but I have some downstream ability to do outlier rejection. So this is, for example, image retrieval, like a Google image search, for example. You can produce a lot of different images, and the user themselves will figure out which of those images they'd like to select. And so a high recall, low precision classifier would do reasonably well in this case. It's not too big of a deal to return 10 times as many images as needed. Now, if you want to have high precision and low recall, there's certain applications that really need to have just a few good matches. So, for example, if we're trying to track the movement of an object or a camera, then we'd oftentimes like to have higher precision than recall, because we can still track the object even if we're not returning all the feature matches. So now that we've discussed some basics about feature recognition, we'd now like to extend this from features to whole images or whole objects. So we can do a lot of things with these features. So for example, if we're trying to do pose estimation, we talked about this last time. You can do, for example, ICP or ransack. The nice thing about feature recognition is that we actually have a better set of points of one image to match to another, to points in another image. And so ransack can oftentimes be accelerated quite significantly if we have good features to begin with. Another approach is that we can try to just basically look at certain patches of an image and see if we have our target image with enough matches of features in that target region. So we basically look into a region of interest, we look to see which features exist in that target image, and then we can look at our source image, and if we have sufficient numbers of matches, then we call that an identification. This, though, only really works for basically two-dimensional bounding box pose estimation. Another thing that we might want to do is label some query, either to classify it or assign an attribute to it, and we have some data set of labeled images that we want to identify. We want to find a match in that data set. So one fairly straightforward thing to do is to try to figure out which image in our data set has the most number of matches. This is sort of like a nearest neighbor approach. But the problem is this is brute force and relatively inefficient. So instead, we'll look at codebook-based methods. These try to identify these features with integers, and then this increases the efficiency of matching. And so one example of this is the simple visual bag of words detector, which we'll talk about right now. So visual bag of words comes from the bag of words approach from document retrieval. The idea is that if you have some document that has some variable number of words, just like in images we have variable numbers of features, what we can do is try to figure out, if we're trying to classify what type of text this is. We might want to, predict its class, or we might want to retrieve a similar document to this sort of query string. So the idea is that we'll come up with a dictionary of possible words. Now, these dictionaries should probably eliminate very common words that are not very predictive of, whether a text means one thing or another. So, for example, small words like a, the, etc. can be eliminated. But, if you're talking about, for example, in this case, it's a description of a movie, then to, try to look at, for example, the word dialogue or romantic or movie, like these are just very significant words. And so you'd want to include this into a dictionary. Now, the bag of words model just counts the number of times a certain word appears in that dictionary. Now, when you want to then represent this text, all you'll do is order the words in the dictionary, and you'll use a feature vector that just looks at the counts of the number of times each word has appeared. So this is a fixed dimensional feature vector, can be calculated relatively quickly for any given text. Now, in visual bag of words, the whole trick is how do we come up with a dictionary? And this is where the codebook comes into play. So what we'll do is we'll take images and calculate these feature points and descriptors. And so we have a bunch of points now in some n-dimensional space. What we'll then do is, rather than treating these points in a continuous space, we'll quantize them using a codebook. This is done in pre-computation with some, for example, large number of images from our database, and we can, for example, do some clustering on these continuous space points and associate points in the continuous space to centers of these clusters. So basically we have a classification of each feature into some number 1 through k. And then what we can then do is take a given image, calculate its features, figure out which code words in the code book these correspond to, and we just count how many of these features, these clustered features, do we actually observe. So we have basically a histogram of these features. Now, we can do all sorts of things with these afterwards. We can try to then find the closest matches. We can also use more sophisticated predictors to try to predict whether we have a match. So for example, a naive Bayes model can be quite effective with visual bag of words. So as an example, there's a technique called FabSlam, which does place recognition and loop closure detection on very long sequences of images, basically video sequences. So here the features are described by image patches. They're then used to build a code book so that these certain, let's say in this case, this fairly distinctive window has several different points on it that correspond to this very distinctive cross-like patch in the image. We can just count how many times we've seen such a thing, and this can be extremely effective for recognizing when you've seen in a location in the past. And so in this case, they've been doing mapping and basically figuring out where a certain camera has been moving by detecting matches of these video sequences along the entire video sequence in the past. So in terms of how to do classification like this, a naive Bayes classifier is a very simple and scalable approach for doing classification. So the idea is that you have a probabilistic model of a class. This was most early used for spam detection. So for example, a class could be spam or not spam, or in the case of object detection, this could be the object class that you're trying to predict. Now these features which derive from the class, they will have a conditionally independent distribution under this naive Bayes assumption, so that a given feature has a certain probability of its output given the class. So for example, in visual bag of words, this could be the word occurrences, or even just binary features of whether a certain code word is observed or not. And with this probabilistic model, what we can then do is do Bayesian reasoning to figure out, given the features, what class is the given image. And in this case, we just use a Bayes rule, which is a relatively straightforward calculation, and this gives us a probability distribution over classes given the features. Now, to train a naive Bayes classifier, it's actually quite straightforward. Essentially, we just look at the empirical frequencies of these features given the classes. We also want to look at the empirical frequencies of the classes themselves. And so we basically just look at counts, and then we look at the frequencies of each of the features given the classes. So this is quite effective in a number of applications. However, it does suffer from various issues. The first one is that, well, we have no information about feature locations. We're just looking at whether they exist. And so it's basically representing an image as the sum of its patches, essentially. And so a visual bag of words approach would recognize this object as well as a completely scrambled version of the object just as well. The other issue is that naive Bayes can't reason about feature co-occurrence. So if two things are highly correlated, it's assuming that they're conditionally independent given the class, but this is oftentimes not true in practice. And so you can use more powerful machine learning models to try to improve your classification accuracy, such as decision trees, support vector machines, etc. Now, in order to reason more about location, you have to incorporate more information into the model. And so there's other techniques like deformable part models that actually use reasoning about the location so that you can, for example, better recognize things like faces. Okay, so as a recap, we looked at object recognition approaches using template matching and feature mapping. We talked about the use of feature descriptors to make this more efficient, precision recall curves for tuning parameters of matchers, as well as visual bag of words. That's it for this time. I'll see you next time.